Welcome to Wireless Future. I'm Eric Larsson, and I'm here as always with my colleague Emil Björnsson. Hello, Emil. How are you today?
I'm great. So it's nice to be back with another episode.
As always. So the idea for today is to do a Q&A on Massive MIMO. And we have a bunch of questions here that we harvested from the YouTube comments, from the blog, and also from emails that we've been receiving. So I think without further ado, we'll get this started. So Emil, the first question is on the 5G standard and why Massive MIMO has not been fully adopted by the standard. And specifically, the question is it true that some companies have started to implement Massive MIMO on their own independently of the standard? That's what the question states, So could you elaborate on this?
So I think the first question is really, what is Massive MIMO that has or has not been implemented? And that is sort of the key issue here, that is there a universally accepted definition of what really Massive MIMO means? I think you and me might be purists saying that this must be implemented in a TDD mode, reciprocity-based beamforming, and all of those type of things. And our books are sort of saying something about how you should implement it. But when you are then taking that to develop a standard based on it, it's hard to say exactly what is Massive MIMO, what is not, and where do we draw the line.
Yeah, of course. But would you say it's true, as the comments suggested here, that some companies are implementing Massive MIMO on their own independently of the standard? I thought that at the minimum, if you implement a wireless technology, it has to be compatible with others so that the terminals can talk with the base station. Or I'm not sure I'm reading the question well here. But
no, I think that is definitely true. But the thing is that I don't think it's independently developed. But I think that the thing to understand is that a wireless standard is like a skeleton that puts the basic foundation of what you need to do in order for the system to work. So what should the base station send to the user? What should the user send back? And have lists of different options that could be utilized there. And then you purposely are not you're not standardizing every single detail. Both because you should be able to make it future-proof, so you can improve implementation in the future, and to give the different vendors possibilities of implementing their own features and making it as good as possible on top of the skeleton that is already there.
Mm-hmm. Yeah, I suppose, especially receiver algorithms, for example, aren't specified in the standard, right? So you could do anything you want there. And while the if we think TDD Massive MIMO, then the canonical algorithms are maximum ratio and zero forcing and all that. But in principle, nothing prevents a vendor from implementing something more advanced. And I suppose the same goes for channel estimation. You could exploit all sorts of prior information to improve on the estimates. So that's not specified in the standard. So there might also be perhaps part of the answer here.
Yeah, so what you standardize is really, you are going to send certain signals that allow you to estimate the channels, and then what kind of estimate you implement, that's up to you. And then you know that you're going to beamform things in the downlink, and what kind of scheme you utilize to select the beams, that's also up to you. As long as there is a mechanism for the users to sort of figuring out how you were transmitting. And that's why even if we are always saying that you only need to send pilots in one direction, you might do it in both directions just because you might not be aware of what kind of algorithms that are utilized in the other direction.
Mm-hmm. Yeah, I see. So I suppose the main items that the standards specify are the format of the reference signals, right? The pilots, and also for FTD versions of Massive MIMO, I suppose the code books are specified. But apart from that, you can pretty much implement whatever you like and that you think works best.
Yeah, sure. So when it comes to these reference signals, they have two options. There is what they call the CSI-RS, or channel state information reference signals, that are what the base station can send according to a codebook and the downlink, and then you can feed back information based on that. And the other option is what is called sounding reference signals, or SRS, that you send in the uplink, and that is sort of this type of uplink pilots that we are suggesting to utilize. And when you implement things, you can choose which of these options you should support.
Yeah, great. All right. You want to go on to the second question?
Yes, so the second question, and all the questions today will be on the theme of Massive MIMO. How are the antennas calibrated in Massive MIMO?
Yeah, so I'll see if I can have a go on that one. That's a good question, and I believe it's a question that still to this day is a source of misconceptions. Because speaking of calibration of an antenna array, there are really two sorts of calibration that could potentially be relevant. Number one is phase calibration from one element relative to the next. And that would be necessary if the array is used to estimate directions of arrival, or to use to beamform into specific directions of departure. To perform such beamforming, you would need to know precisely what does phase 0 mean at each one of the elements, because the whole idea of directional beamforming is that you phase shift the signal and have complete control over the relative phase between neighboring elements in the array. That's how beamforming works when you shoot power into distinct angular directions or spatial directions. Now, TDD reciprocity-based Massive MIMO that we argue for and that we have in our textbooks, for example, does not require phase calibration in that sense at all. But then there is the second sort of calibration, and that is reciprocity calibration, which means that we know the relative phase between the receiver chain and the transmit chain at each one of the antennas. So no need for knowledge of anything relative between the antennas, but a need for knowing the relative phase, what it means for phase to be 0 on uplink versus phase to be 0 on downlink. And that reciprocity calibration is required for TDD, reciprocity-based Massive MIMO, to work. And it can be accomplished through a variety of means. I know of experiments where they've used like mutual coupling within a large array between the elements to perform this calibration using very clever schemes and mathematics and regression fits and so forth. It can also be accomplished by having specific transceivers dedicated to the calibration task. And there's a wealth of methods here, but that calibration is necessary. And I think it's worth reiterating this point that there are two sorts of calibration, and for TDD Massive MIMO, it's only the reciprocity calibration that's needed. And again, in contrast, when you want to beamform into distinct angular directions in space, then it's rather the relative phase calibration that would be required.
Yeah, when it comes to that, I was in conversation with some hardware people the other week, which was really about people who are used to working with what we call phased arrays, where you have this type of phase references that you know, and which are typically utilized just to beamform in different angular directions. And they were like saying that, look, if we're gonna illuminate different parts of the countryside, then we need this type of information, and so complicated in what you're suggesting with Massive MIMO, where we in every millisecond we need to send the pilot so we can learn the channels and for a brief moment of time phase align the signals to a certain point. And in a way that is a valid argument, but on the other hand, we have built wireless standards for decades now where we are sending pilots every millisecond, so it is not a practical problem.
No. It's been demonstrated all over again, right, that reciprocity-based Massive MIMO beamforming works with pilots in every coherence block. So again, but there seems to be, a tendency, even to this day, to conflate these two different types of calibration, where for the TDD reciprocity MIMO, only the second one actually has any importance.
And then when it comes to the uplink downlink reciprocity there, this has to do with the hardware components, right? That you use different pieces of hardware partially in the uplink and the downlink, and they are not calibrated with each other.
Yeah, yes. They're different chains of electronics to start with, and they have their built-in imperfections, and they have components whose characteristics vary with temperature and perhaps age with time and so forth. But that said, this reciprocity calibration doesn't have to be performed very often. It's not like you have to do it every millisecond. You might have to do it a couple of times per minute or something like that. Depending on the air quotes like quality of the hardware components, then you have to do it less or more or less often, but in terms of resources required, it's negligible.
Yeah, and then I believe for the base station, it shouldn't be a big issue because it's turned on continuously, and you can use this additional information now and then to calibrate it. But if you're turning on and off your phone, or it sort of goes down to sleep mode, and then you open it up again, then I guess the phone might not be able to be calibrated between uplink and downlink all the time. Is that right?
That's a good point, but the terminals don't need reciprocity calibration for reciprocity-based massive MIMO to work. At least not with single antenna transmission from the terminal.
I guess you
so
might
that might be less of an issue. Yeah.
You might have to send pilots in both directions then, so that you can sort of rotate your constellation diagram in the downlink as well, so you get the right.
Right. You'll need if the terminal isn't reciprocity calibrated, then you'll need to have a reference signal on the downlink to rotate the signal constellation, right? Although that could also be solved by other means, blind algorithms, but yeah. I don't know, might lead too far to go into here. Yeah, all right, great. So I'll move on through the list. The next question we received is on UAVs, so like flying vehicles and drones, and whether Massive MIMO can be deployed on a UAV, or can we use Massive MIMO to serve UAVs?
Yeah, this is an interesting question. So I think UAVs are these unmanned aerial vehicles, which we are normally calling drones. And so both of these type of options are things that people are considering, at least both to serve UAVs or to put a base station on a UAV. And if you think about putting the base station on there, I think one of the main issues with drones is that the time that you can fly around before you have to go down and recharge your batteries is relatively short, because it's sort of a heavy piece of thing to start with, and then if you put additional equipment on it, then it becomes even heavier. So I was looking at this 64 antenna 3 gigahertz band and base station antennas that are used today. They weigh 60 kilos. And if you go up to the millimeter wave band, then I think that 13 kilo, the street macro base station that I mentioned in the last episode. So those pieces of hardware is not what you're going to put there. And then I guess in addition to that, you will have a heavy power consumption also for all the processing and transmit powers. That said, I think that there are use cases for base stations put in a UAV. You sort of send them up, you are watching the world from another angle, and in that way you can provide better coverage in certain areas. And in particular, when you are in troubles in the regions, you are looking for people in the countryside that have been stuck somewhere. I guess you can improve the coverage by sending a base station, but it should be the simplest type of base station that you can imagine. You don't want to use it for.
So you're saying that Massive MIMO base station, the way we think of it, at least for lower frequencies, is too clumsy to attach to a UAV because it's too heavy, and you'll need really a big helicopter or something to carry it.
For the time being, then you never know how much you can shrink these type of things in the future, and maybe if you can cut down on requirements on out-of-band emissions and things like that, you can simplify the hardware a lot and use like UE hardware instead, things from the handsets.
Yeah, right. All right, well...
then we had the other part of the question, right? If we can serve them. And this is an interesting thing. I wrote a paper with some people at Nokia a few years ago where we were talking about that particular thing, because I think the base station that are normally utilized, the ones that are not doing beamforming, they're just down tilted a little bit, and then you transmit the beam down to the Earth. Then the problem is that if you have a UAV flying right above it, it will not be inside of the beam that you are focusing towards the Earth. So if you just try to connect it to the mobile network, what will happen is that you probably will have a base station that is much further away, that happen to have its first side lobe pointing upwards that is covering you partially. And since it's line of sight, you're typically going to see the base station in these cases, then you will still get reasonable service, but you will sort of blast the entire Earth around you with a lot of signals, because you're connecting to something that is much further away, you increase your power, and you are creating a lot of interference to the ground. And I think here, the beamforming capability of Massive MIMO array can be utilized to sort of send beams up to the UAV just so that you can send it down to Earth.
That's an interesting point. I mean, I always thought of, like, for this use case, communicating with UAVs, then you'd have like a dedicated ground station with the antennas, because I mean, antennas pointing upwards towards the sky, right? I mean, antennas, I mean, they're like individual antennas in the array, because these antennas are going to have some intrinsic gain, and then you probably want that gain to have its main pointing beam direction upwards rather than downwards. But obviously one could think of using like existing cellular infrastructure as well to communicate with the drones.
Yeah, so I think that was a starting point for this work, that some operators were interested in knowing if we would buy your new Massive MIMO equipment, can we use them to serve things flying around in the sky as well, or will we have to have dedicated equipment? And as you say, it might always be better if you can put something that is pointing upwards, but it seems like this could work to a good extent.
Yeah. All right, good. You want to move on to the next question on the list?
So when reading about Massive MIMO, I come across a term called channel hardening. Could you explain what it means?
Okay, so I'll do this one. So channel hardening, this is a basic thing that's explained, I think, in our books, among others. And so here's the main point, that think of a terminal with a single antenna receiving something in the downlink. Now, that terminal is going to see the data symbols through an effective scalar channel. And that scalar channel is going to be equal to the actual physical channel, which is m-dimensional, with if we have an array with m antennas, it's m-dimensional. So it's like a vector with m elements, times an m-dimensional beamforming vector. So it's like an inner product or scalar product between two m-dimensional vectors, right? And that scalar product is the sum of m variables. And these variables are like fluctuating and random because of the fading. So think of it as like this effective scalar channel that the terminal sees the data through is a sum of m random variables. And then you can argue, like with the law of large numbers or the central limit theorem, that if m is large enough, then this number is going to stabilize statistically. So it'll be very close to its statistical average, to its expected values. It's fluctuate very little around its statistical average. That's what channel hardening means. And the implication is that the effective scalar channel that the terminal sees is rather independent of time, and it's independent of frequency. So that with OFDM modulation, for example, and every subcarrier in the system gets to see the same effective gain, more or less. So this simplifies a lot of things. I mean, one thing is it simplifies resource allocation, because there's not much point any longer to schedule users at different portions in the frequency domain, or in the time domain for that matter. And it also simplifies mechanisms like power control, because the effective gain stabilizes and becomes equal to its statistical mean. Then there is no point in adapting the transmit power to individual fading realizations any longer. So I think that's really what the question here.
Yeah, there were a follow-up question that was saying, so do we need to update the power control in every coherence block since the channels are changing at that pace? Or if not, how often do we have to update or run our power control algorithms?
Yeah, so the power, I think that's largely a misconception. I mean, so because of the channel hardening, then the effective channel gain, and for that matter also like the effective gain of all the interference, will be substantially independent of frequency and of time, so that it's enough to perform power control, compute power control variables or coefficients only when the large-scale fading changes. And now with a caveat that if there is scheduling in the system such that users come and go quickly, then that will affect the interference level, and it will affect the, say, optimal power control as well. So I think the answer is really here, well, recompute the power control whenever the large-scale fading changes, which is very slowly, and or whenever the scheduling assignments change significantly.
Yeah, so it probably will be the scheduling or a few high mobility users that will be changing these type of things. And then I would guess that this also will be that it's just going to be some of these statistical parameters that is going to change at the time. So you can sort of start from your current solution and evolve it. It's not going to be totally random as it would be in a scenario with a lot of fading that is affecting your gains.
Yeah, probably, right. So,
and when it comes to this, I think one misconception that I've sometimes come across is also that people are saying, oh, so due to channel hardening, we don't need to estimate the channels so often anymore. But that's not true.
No, that's really, I think, a misconception. You want to explain what's going on here?
Yes, so it's sort of, in order to get that scalar channel that you mentioned, which was the inner product between the physical channel and some kind of vector representing your beamforming transmission, you need to, so the channel is changing as quickly as it does in every wireless channel, and then you are reselecting your beamforming vector based on new estimates of the channels, and then when you form that in the product, then every time you have done that, you get approximately the same value, but you still need to learn the channel.
Yeah, you still have to learn the channel for the purpose of beamforming in every coherence block, right? I mean, that's the whole point of the reciprocity-based beamforming. You actually do that. So in a way, you air quotes like track the channel or re-estimate it on a time scale, which is the coherence time of the actual physical channel. But notwithstanding that, the effective scalar gain of the channel that the terminal sees in the beamforming is very stable and close to its statistical mean. Yeah. All right, good. I think we'll move on through the list. And here's the next question. So it is about EIRP, effective isotropic radiated power, and whether that is an issue when applying Massive MIMO in practice. You want to answer that, Emil?
Yes. So this is sort of a measure of, say that when you're transmitting, you always have a directivity of your signals. And if you are considering, okay, what is the direction where I'm putting the strongest amount of energy? And then you would consider a transmitter that was sending that information isotropically, so in all directions, how much power would that one consume? And in reality, we are never consuming that power because we have the directivity, but it matters in particular when we talk about out-of-band emissions. And that's something that we've been talking about as an important aspect earlier as well in the previous episode. So typically when you are buying a license to use a certain amount of spectrum, you have strict requirements of how much emissions you're allowed to put outside your band. And then the important thing is not how much power you're transmitting with, but what is the strongest power that you get in a particular direction. And that's what this EIRP is specifying. And this can be very complicated to actually measure. So if you just have one antenna, you might know from physics how it's going to behave. But then you put together a big array, and then you should put it into a measurement room. And then you know that as large as the array is, the far field becomes further away. So you need to have a bigger room so you can actually measure what is the actual directivity that you are getting in practice, and not only what the physics are telling us. But I was looking into this when it comes to the Massive MIMO, because it's really about that when you put more antennas together and you're transmitting, say, with the same total power, you get more directivity. So you get this type of issue that if you want to keep the transmit power fixed and you increase the size of your array, well then you get more directivity. And if you have a license that is saying that you have a certain maximum EIRP, then the more antennas you use, the more you need to cut down on your power to compensate. So that could be a practical problem. And that opens the question, when they are selling now 5G licenses, what type of out-of-band requirements are they going to be? Because you're really sort of designing this for the worst case, and if that never happens, well, then should you care about these other band emissions in the worst cases? I was looking in Sweden, so we have a 5G license auction that it will soon start, and there, when you're talking about the 2 and 3 gigahertz band, if you are putting up a base station with a fixed antenna, then they say that you're allowed to have an EIRP of 68 dBm per 5 megahertz of spectrum. Or if you use a massive MIMO array, it's only 47 dBm per 5 megahertz, which means 50 watt. But then they are not measuring the EIRP, but instead the total emitted power. And then 68 and 47, well, there's a say 21 dB difference between that one, which is sort of saying that, well, as long as your array is not having more than a 20 dBi directivity, it's more or less the same type of requirements. But if you
so 20 dB directivity is like 100 antennas, right?
Yes, if there would be omni antennas. I think this type of Massive MIMO arrays where they have like 64 elements, 32 in each polarization, and the polarization are behaving differently, they might have 24 dBi directivity because they sort of are 32 in each polarization and 9 dBi intrinsic directivity of each element.
Yeah, sure. I meant the gain from having an array in itself is 20 dB if you have 100 antennas, roughly speaking.
Yeah, so I think that what this really means is that in Sweden, the regulations are saying that you're allowed to have a little bit more directivity if you put up a Massive MIMO array as compared to what we are used to. But if we are having requirements in the country that are going to be the same, so you're not allowed to increase your directivity, well, then that effectively means that you are forced to transmit with less power, which doesn't have to be a problem because Massive MIMO is really about pointing the energy where it should be. So if it's the same requirements as you had in the center of your cell before, well, now you can deliver that towards the cell edge as well.
Would this be an issue if we had larger arrays? I mean, there's 20 dB here. What if you have like 1,000 antennas? Or, I mean, that'd be like 30 dB, right? Or 10,000 antennas. I don't know whether Massive MIMO with 10,000 antennas is practical or not in any sense or even useful. But just for the sake of argument, suppose it is, then that would be like a 40 dB increase in the array gain. So would that be an issue then with these numbers that you suggested earlier?
Yes, so if you have a requirement on your EIRP, then it will be a problem that you will be forced to cut down on your power. If you have a license that is not specifying the EIRP, or maybe a combination of them, then you might be allowed to still use the same power or not cut down proportional to your additional array gain. But it sort of shows that we shouldn't expect to use Massive MIMO in every country to increase the signal-to-noise ratio. But it should be roughly the same as it would have been if you have a fixed beam in the right direction. It's rather about that you can multiplex multiple signals at the same time and frequency.
So the short answer here is that EIRP has to be considered as a factor in the game when deploying Massive MIMO, especially, I mean, the larger array, the more of an issue it is, right?
Yeah, so you are essentially taking, to compute the ERP, you take your total power in dB, you are adding the strongest directivity in dB, and if you have a strict requirement, well, if you increase one, you have to cut down on the other.
Yeah. All right, good. Shall we move on the list? We have a couple of more questions to go, I think.
Yes.
You want to do the next one?
What is the future of wireless power transfer? Can Massive MIMO push its limits?
Yeah, so let's see if I could give an attempt on that one. So wireless power transfer is a highly exciting technology. I mean, as the name suggests, the idea is to transmit power wirelessly. And now the difficulty with this in general is that we don't want high power transmitters and then be as human in the vicinity of them, right? I mean, you wouldn't want like a kilowatt of transmitter and then stand a meter from it. It'd be like running the microwave with the door open. So looking at like state of the art in wireless power transfer, there are transmitters that emit about a watt, and then within a meter or two from them, you can harvest like a milliwatt. And a milliwatt is enough to keep some electronics going, right? So now the question is whether a directive transmitter could significantly extend this range of a meter or two. And it seems the answer is yes. I mean, as always, the difficulty with getting a MIMO transmitter to be effective is to get the array gain, which in turn requires channel state information at the transmitter. So, I mean, in plain English, the MIMO transmitter would have to know in what direction to point the beam, right? So there would have to be some exchange from pilots, or this little device that we want to beam power to would have to transmit something, like a small spark or a small air quotes like pilot or reference signal, so that the MIMO array could determine where to point the beam and where to direct the power. But in principle, I mean, if you think of it, with 100 antennas at a transmitter, you get an array gain of 20 dB, and in free space line of sight, 20 dB is that's 100 times, so that's 10 times in range, right, in free space line of sight. So and that's again in free space line of sight with a path loss exponent of 2, whereas if we are indoors, then the path loss exponent is probably smaller because there is rebouncing against the walls, and I mean the energy doesn't disappear and doesn't radiate away omnidirectionally, and just disappears in space. So the potential range extension might be even higher there. So I think the short answer is yes, Massive MIMO can definitely push the limits of wireless power transfer. I think we'll be seeing this happening, and I'm especially optimistic of distributed MIMO solutions like radio weaves and radio stripes and that type of technology, where I mean the walls might be entirely covered by antennas that can operate coherently together and beamform and so forth. So I think it is an exciting direction where we are likely to see a lot of new developments in the coming maybe 5 or 10 years.
Yeah, no, I certainly agree, and this might be a use case. If these devices are relatively static, then it might be a case where like traditional phased arrays might be more convenient, because if you know that the device is not going to move around, well, then you have a line of sight channel, maybe it's enough to just learn the angle of arrival there and beamform in that direction and continue doing that for a very long period of time.
Right, that's a good point. I mean, the channel coherence might be very long, right? If the device you want to beamform is stationary, then it might be enough to learn the angle of arrival or angle of departure to it once and for all, almost. So there's certainly a lot of tricks and algorithmic technology that could be developed and leveraged here. Yeah. All right, very good. So I'll go to the next question, and perhaps you could have a go on that, Emil. So will analog and hybrid beamforming solutions be replaced with digital solutions in the future, or is it worth it or not to replace analog and hybrid with digital?
So I'm definitely a big supporter of digital solutions, and I believe that in many use cases it will be replacing things. But then it's also easy to be too enthusiastic about new prospects. And I think from a sort of a practical or economical perspective, we should think about that. Okay, what if you compare, say, a phased array that can just beamform in a particular direction, just send one signal at a time, so that is some kind of analog type of solution, then what can you gain in additional with Massive MIMO? Well, you can serve multiple use at the same time or frequency. You can deal with complicated propagation environments. When there are maybe 10, 15 different directions that are leading to the user, and you need to make sure that for every user you get the right combination of those ones. That's essentially what our processing are implicitly doing. But if you are in a scenario where you don't need that feature, say that we have a lot of base station on the countryside, rural areas, and they are used to beamform to one house or to one highway and follow particular directions, and there is not much variability, there is not much usage, then probably you can get away with simpler solutions, and they will cost less, they might consume less energy, and be more efficient energy-wise and cost-wise.
So you're saying you're suggesting there's a market for both solutions here, right?
Yeah.
Like a budget Massive MIMO would be some hybrid solution that works reasonably in line of sight sort of propagation, and then when you really want to get high performing hi-fi Massive MIMO, then you'd go for fully digital. That's the key then.
Yeah, and I remember when we were starting to discuss the Massive MIMO technology with people in the industry, they were also saying that, look, we are looking at our nationwide system simulators, and look, we don't see much gains in Massive MIMO. It's only in like 5% of the cells. And those are, of course, the 5% of the cells that are driving out of the traffic that are in the cities. And there is the first use case of Massive MIMO. But then in the countryside, you might have a lot of base stations that are not limited by their capacity. They're only there to provide coverage. And for those sorts, it might take a long time before you actually benefit from a digital solution.
Yeah, I mean, again, what you're saying is one of the main selling points of Massive MIMO with fully digital beamforming is that we multiplex many users at the same time, right? And that, of course, rests on the assumption that there are users that we want to multiplex. So yeah, it's a good point.
Yeah, and the second selling point is that you can deal with complicated propagation environments. And if you have a very simple one, well, then you don't get that benefit either.
Yeah, right. Oh, well, we got, I think, 2 more questions to go here on the list.
So I have one for you.
Do you want to go on to the next?
Yeah. So talking about beamforming, so when we are applying things like zero forcing and things like that, when you're trying to serve many users at the same time, and then you're solving a, say, matrix inversion, and you figure out how much power and which phase you should put on different antennas, then you are essentially getting different amplitude and phase on the antennas, and those amplitude variations on the antennas, I believe those should sort of create more dynamic variations in the signal power on each antenna, which is a problem when it comes to power amplifiers that prefers to have small variations, because they can't be built to have a linear amplification everywhere. So is this a problem that we are, with Massive MIMO technology, increasing the dynamic range and we get more power amplifier issues?
I mean, it is a legitimate point, I think, but let's also remember that one of the main culprits here in terms of creating high peak to average rate is OFDM modulation, right? Then, of course, if you put some exotic beamforming on top of the OFDM, it could aggravate the problem. That's certainly true, and it is an issue. I mean, because in practice, you want not too high peak to average ratio. High peak to average ratio forces you to back off your power amplifiers, which in turn reduces power efficiency and so forth. And if you don't do that, you'll get out of band emissions. And as we know, out of band emissions can be disastrous. And
that's where you have this EIRP type of requirements on those ones as well.
With a MIMO transmitter in a static environment, the out of band emissions are beamformed and directive. In a fading, in an environment with high mobility, there might be some averaging effect depending on if you average over time or not. But in a static environment, these out of band emissions are beamformed into specific directions, and they could easily, if a victim stands in the way there, then you destroy the link for him. So I think this is a legit concern. And to address this properly, we have to model the transmission carefully and accurately. You basically have to go to continuous time models to really model properly the peak to average, and that's a topic where there isn't a huge amount of academic work done on it. It seems to me to be a problem which is very well recognized among those who work on implementation and standardization and so forth, but hasn't been very much mainstream in the academic Massive MIMO literature so far.
Yeah, no, so I think the OFDM modulation, as you're saying, is already creating a lot of variations, which is something that one might not think about when only dealing with the discrete time models, because you can say, oh, I put equal power on all the subcarriers, so therefore I get equal power in the time domain, but you don't, because when you are taking your inverse FFT, you're sort of creating a time varying channel that is very quickly changing.
Yeah, I mean, there's a FFT, and then there's a pulse shape you put on top of all this, right? And continuous time pulse shape that also. So it's a fairly intricate matter to model properly. Yeah.
Yes, and as far as I've seen, you add some dBs extra in variability by doing this type of pre-coding methods. At the receiver, it's not the same issue because you can apply everything that you want afterwards, but at the transmitter side, this problem arises. And I've seen a few solutions where people are trying to add some constraints on how they select their pre-coding to deal with some of these issues.
Yeah, and I think there's further room for algorithmic development in this field. Again, I mean, there isn't a huge amount of literature on it, but it is a highly important problem in practice. Yeah, very good. I think we're approaching the end, and I'm gonna go on the last question. Perhaps you can answer. So the last question here is on metrics of performance that are used in wireless comms, and I think the point is that classically or conventionally, I mean, a lot of folks like to use capacity and some capacity and spectral efficiency and so forth. And the question is, well, first, how does it relate to OFDM, but also, are there other metrics that potentially are as relevant as capacity and rate and some capacity? You want to elaborate on this?
Yes. So I think one can sort of simplify this discussion by dividing into two categories: when you send long blocks of data and when you send short blocks of data. So when you have a short block of data, which might be what you put on one subcarrier or multiple subcarriers in the OFDM system, but say that it's only a few thousand bits or less than that, then you're going to code it with a channel code, and even if you have a state-of-the-art channel code, there will be a probability of error that you need to live with. And then that is sort of your performance metric. You pick a certain modulation scheme and coding scheme, and then the bit error rate or maybe the block error rate for entire code word is what matters. Because if you fail with that one, you will have to retransmit.
Yeah, I think in terms of metrics, I like to think that there are three regimes essentially, right? First, there is a Shannon capacity regime where you have very long blocks.
Yeah, that's a long block case.
10,000, 100,000 bits, such that Shannon capacity and bounds on it, like achievable rate and all this, numbers, are legitimate proxies of performance. And then second, there is the finite block length regime, where the approximations and bounds from finite block length information theory are good proxies for performance. And third, there is, and that might be when you're down to maybe 50 bits or something like that, right? And third, there is a regime where you have only a handful of bits, like control signaling in certain cases, where the bounds and approximations from finite block length information theory just too loose. And the only thing we can really do is to measure error probability empirically. So certainly I think the question is a very good one. I mean that although perhaps the bulk of the bits that will be transmitted over the area interface are part of very long code words, such that some capacity is the metric to go with, there is also a good deal of other types of traffic for which some capacity and Shannon capacity aren't really the right way of quantifying performance, and where partly other tools are available.
Yes, and I've also got the impression that many of the wireless systems are built so that even if you're going to transmit a large chunk of data, so you could be in the regime where you have large block lengths, they are still deciding to have short block length to keep the decoding latency down, so you can decode things quickly, and also to have sort of the flexibility that you can transmit whenever you have a possibility, and you make sure that what you have received can then be decoded, and then you wait for another point to get sort of these best effort types of networks where you're sending some chunks of data, even if you know that you're going to transmit gigabytes of data eventually.
Yeah, certainly. I mean, latency might be determining sometimes how long code words that you can afford to use, and latency requirements thereby might force you to operate in a regime where you have shorter block lengths than you would nominally have if you consider your whole data stream. Yeah, it's a good point.
Yeah, and talking about capacity there, so the channel capacity is the maximum number of bits per second or bits per second per hertz of bandwidth that you can transmit, ideally over all possible ways of transmitting. That's essentially what it's saying. And optimal then means that if the length of your code block goes to infinity, you can achieve this one with no error probability at all. So it goes to zero. And then related to that is a rate or spectral efficiency. Those are often used interchangeably to say that this is something that we achieve with a practical scheme. It's a number smaller than the capacity. And rate can have multiple meanings. It often means either bits per second or bits per second in hertz. And spectral efficiency always means bits per second in hertz.
Yeah, very good. All right,
Yes.
Emil, I think we are through with the questions, or are we?
Yes, I think these are all of the questions that we received this time on the theme of Massive MIMO. We will come back with further Q&A videos.
We certainly will. And as always, feel free to send us comments or questions or suggestions for topic to talk about on the podcast. And with that, thanks a lot, Emil. A great conversation. And to everyone listening, thanks a lot. And don't forget to like and subscribe us on YouTube. And see you next time.
And Happy New Year.
Happy New Year.